Welcome back. Now we're going to talk about the tangent functions graph. So again, we have to use our unit circle logic. Just to refresh what we learned about sine and cosine, we want to recall that we have these two continuous functions, our sine and cosine. Both are period 2 pi, both have a domain of all real numbers. The range for each is between -1 and 1. These parent functions have an amplitude of 1, and then sine is odd and cosine is even. So we've got our sine graph, which we know how to draw that curve from 0 to 2 pi, as well as our cosine graph. Okay, so now we're going to talk about tangent. So we'll do the same thing. We can plug all these values in and determine what the tangent of each of them is using the unit circle. Remember, when you think about your unit circle and you have some arc length you're measuring, pi over 6, each of them has an xy ordered pair. Remember, x represents our cosine and y represents our sine. So for example, at pi over 6, we should have √3 over 2 and 1/2. So sine of pi over 6 is 1/2. Cosine of pi over 6 is √3 over 2. And tangent is sine over cosine. So tangent at pi over 6, tangent of pi over 6 is going to be 1/2 over √3 over 2, which simplifies to 1 over √3, which then of course rationalizes to √3 over 3. So just a little also refresher on some unit circle logic. So essentially we need to find tangent for all these different values, and these are just different values on the unit circle, and I specifically set it up with these values just because I know they're going to kind of give me an idea of what's going on with my graph. But of course, I could use any radian measure on the unit circle. So let's start with, say, tangent of 0, right? Tangent of 0. 0 on my unit circle is right here. My ordered pair is 1, 0. So if I were to figure out tangent, that would be sine over cosine, or y over x, 0 over 1, which is 0. How about at positive pi over 2? So pi over 2 is going to be up at 90 degrees, and we've got the ordered pair 0, 1. So at pi over 2, if I put sine over cosine, I would put 1 over 0, and I'm not allowed to have 0 in the denominator, so a number divided by 0, that would give me undefined. Lastly, over here at pi over 4, I know that my ordered pair is √2 over 2, √2 over 2. So if I put sine over cosine, I put that value over itself, I'm going to get 1. Now, working through this, you'll get similar numbers, but you could get a -1 because remember, depending on which quadrant we're in, tangent could be negative. We know that tangent is positive in quadrant 1 and in quadrant 3. We say all and tangent, those are the quadrants where we have it positive. So I'm going to pause the video, fill out the rest of my numbers. I encourage you to pause, make sure you've got those numbers down correctly on your paper. And you're back, you paused, you're still here. You found all these values. So we start to notice a pattern. And at the pi over 2's, positive pi over 2, negative pi over 2, 3 pi over 2, these two are the same on the unit circle, we get an undefined value. And that is because at all of these undefined values, at our pi over 2's, we end up with vertical asymptotes. So the way I have divided my xy axes here, we've got pi over 4, pi over 2, pi, 3 pi over 2, and 2 pi. So those intermediate marks are my fourths. And I have this going from +1 to -1. Over here on the left, we would have negative pi over 2. So what we just said was at pi over 2, we have vertical asymptotes. All right, and if we look at plotting points between, say, negative pi over 2 and positive pi over 2, we get something that looks like this. And of course, this looks linear when I plot these dots, and I could find many more x values in here that would give me corresponding y values. But what we will learn is that tangent behaves sort of like this, and it buddies up to its asymptotes, which is the nature of what occurs at an asymptote. So looking at this again, in the next quadrant, we would get a similar behavior, and it would just keep going infinitely, even though this goes off of the screen there. So we would maybe see one occurring up here as well. So this is what our tangent graph looks like. What is the domain of tangent? What is the range of tangent? Well, the domain we have to think about quite a bit. So let's think about our domain here, because we have a lot of undefined values and we need to determine how we're going to write this. So the way I'm going to say this is that x is going to be a real number. However, we have to leave out certain multiples. So what we know is that x cannot equal some pi times k multiple of pi over 2. So at our pi over 2's, right, here's a pi over 2, 1 pi over 2, or negative 1 pi over 2, positive 1 pi over 2, 3 pi over 2. What am I adding? I'm adding 1 pi, right? 1 pi over 2 to 3 pi over 2. We'll say pi over 2. I'm going to add some value to get 3 pi over 2. What is that value I'm adding? I'm having to add halves, so that would be 2 pi over 2, and 2 over 2 is just 1 pi, okay? So anywhere except at these pi multiples. And so k, when I use this k value here, k is just a integer value. So k is an integer. We can write it with symbols. K is an element of the set of integers, or k is an integer. And what is the range here? So range are the possible y values. And we say, well, does the graph go up and down forever? And it does. So my range, my output or y values, are the set of real numbers. And of course, on the the first two trig functions, sine and cosine we looked at, we had a period. I want you to notice the period for tangent is a little different. The period for tangent is only pi wide. All right, so tangent has a period of pi. So on the next slide, I'm going to pull some stuff in, and we're going to kind of look at the graphs of the reciprocal functions as well. So we just talked about tangent, and you do need to know this information about tangent for this class. This is stuff you want to recall. So you want to know that period. You need to know the domain has these values that we leave out. And then the range is all real numbers. Now, cotangent has a very similar domain, but instead of pi over 2 plus pi k, it's 0 plus pi k. And then cosecant and secant, theirs are a little bit trickier. So let's just look at the graphs of those without actually doing them by hand. So this red graph, this graph is the curve of y equals cotangent x. Now, we don't have a cotangent button on our calculator, so if we wanted to graph that, we would graph y equals 1 over the tangent of x. And so you can see, these red curves, these represent cotangent. And what I want you to see is there's a relationship between cotangent and the gray graph, which is tangent. So here's our cotangent function. It still has a period of pi. We have vertical asymptotes at 0, plus 1 pi, plus 2 pi, minus 1 pi, minus 2 pi. All right, the next one we'll look at will be secant. So here we have secant. Secant is reciprocal to cosine. So again, considering how we would graph this, if I wanted to graph y equals secant of x, if I needed to type that into my calculator, I would type y equals 1 over cosine x. So you see our gray cosine graph is occurring right in here. And then you see this relationship with its reciprocal graph, secant, right? So cosine and secant are reciprocal, and we've kind of got this relationship where they bounce off of each other. And you'll see something very similar with cosecant, which I'm going to pull in now. So the last piece on this page, we're going to talk about cosecant being reciprocal to sine. So y equals cosecant x. If I wanted to graph that in my calculator, I would need to type 1 over sine of x. So again, I see that sine curve from 0 to 2 pi. And then I notice my cosecant graph, that reciprocal function is bouncing off those maxes and mins. And of course, we've got these vertical asymptotes. So for cosecant, secant, and cotangent, I don't expect you to know the properties of those, but I do want you to have a fair understanding of what the graph looks like, or at least know pretty quickly how to type this into your calculator and create the graph. So in the past, in this video and the video before this, these past two videos, we only talked about the parent function, right? We didn't apply any transformations. We didn't stretch vertically, stretch or shrink horizontal. We didn't have any reflections over the X or Y axis or any shifts up, down, left, or right. So in the next section, moving forward, we're going to talk about transformations. And the transformations are really just the same as everything you learned in algebra. We're just going to take them and apply them to trig. All right, well, I look forward to checking in with you guys in the next video.